If you're so inclined, let's start there. So, homo in the US has a lot of connotation that you don't want to know. I told you some configurations experimentally as to how to construct approximately homogeneous turbulence. And the first non-trivial thing to do, say I have the flow everywhere, is to consider a velocity component in this direction, say I could be any of the three directions, at a position x, and another, let's say, velocity in the component j at a position x prime, which is equal to x plus r. So this being the separation vector r. So you take velocities between these 2 points, you consider the product, and you average the product as you move this configuration around from one position to another. So we are considering then this thing I call Rij, which is a function of various things, which is equal to ui at x times uj at x, and the average value of this. Okay. In homogeneous turbulence, because the value of this average quantity depends on the configuration and nothing else. In particular, it doesn't depend on x or x prime or whatever, but it only depends upon the separation vector r and t. If you average, it's not there either, so this is just r. So as I say, sorry, excuse me, ui x, j at x prime, it's already. Now you want to derive an equation for this thing using Navier-Stokes equations, and the process is very similar.
What is it?
What's that?
What is x bar? X prime?
With this one?
No, the other x.
Sometimes I put tilde, sometimes I put bars, but they're all telling you vectors. This bar here?
Prime is just x. That is A1.
This one here?
He's asking what is x prime. It is just
X prime is this one here. Jeez, I'm sorry, that's a mistake. Total mistake on my part, confused you completely. So that's some, with respect to some origin, this is x, that is x prime, and that's a separation vector. Depends only on this. So now you can derive the equation for this pretty much similar as we did before. So you have an equation for ui, so delta ui d dt, and you have d uj dt, and you multiply this by uj prime meaning, let me first say something else before I even begin to do that. I mean, in homogeneous turbulence, the mean flow is very trivial. It's either constant velocity that is moving everything along, or there is no mean velocity at all. So if there is no mean velocity at all, just the capital Ui that we considered before would be 0 for all I, or it might be some constant, but if it is a constant, it doesn't matter anymore. You just subtract out the constant and you have just the fluctuations. So initially in the morning, I call this ui for the mean, and for the fluctuations I use the prime. But now I'm going to drop the prime because you only have only have fluctuations here. So when I write something like that, it actually means just the fluctuations in here. And sometimes it is convenient to call uj at x prime as uj prime, just to be, I don't want to write the argument all the time, but you shouldn't think that this is a fluctuation and this is a total quantity and things like that. Is that clear? So that's what I will do. And I want to derive the equation for this. So as I said here, I have an equation for ui and an equation for uj, and multiply this by uj, multiply this by uj prime here, this is uj prime, and then you have all the terms on the right hand side. You rearrange them, which I would be happy to do. I have them here, but I think it's better that I skip all that and write the final equation for you. So the final equation is d by dt of rij equals d by drk of ui uk uj prime. This is ui at the position x, uk at position x times uj prime, uj at position x prime. That's what it means. So ui uj prime uk prime. So that's the third order quantity. You have a second order thing, a third order one here, plus the pressure terms will be very simple. D of P uj prime over d ri minus d P prime ui or d drj plus 2 nu Laplace squared rij of r and t. So this Laplacian here is simply d squared over d rk or something like that. Okay. It all refer to the separation vector. What I have done is there is d by dx here and d by dx primes there, and I have converted them all to a differential with respect to this separation vector. So that's the equation, which is not as hard as the one before, but it has all the terms in it. This is the nonlinear term, this is the pressure term, and this is the viscous term. So let me tell you what some general properties of Rij are. Rij is, as say, the product of these two velocities averaged. If you shrink this, that is, take the product between two velocity components at the same position, that one will be the largest of all the possible values you can imagine for other different values of r. In other words, Rij of 0 is always greater than or equal to Rij of r. So let's say I fix I and j and take their product, so it will have some component of this will have some shape like that. It will decay. It will have a maximum value somewhere in the middle, and then it will a maximum value at 0, and then it will go down. So that's one aspect of it. And just as we defined Rij, you can define a Fourier transform of that. A Fourier transform is you can do whenever this function satisfies some simple properties. So the Fourier transform I can define in this fashion. Take Rij. I will interpret all this for you later on. Is equal to, say, phi. I'm introducing this as the Fourier transform of this. K is the complementary variable to R times e to the power I k r dk. Okay. So you could do, for instance, a Fourier representation of Rij. If you have a fixed domain or something like that, you can represent it by some Fourier series or something like that. But this is a more reasonable way to do. And phi ij will be the Fourier transform of Rij. So this variable here is the conjugate variable to R, and that is the wave number. So in a certain size R, you can fit a certain number of waves, and the number is simply related to this K. So something like that. Now there are other things you should know. For example, drij or dri, which is equal to drij drj. This is equal to 0. Now, how is that 0? Although all of this is not necessary for us, because I'm only looking at a higher level, it's useful for you to know how this comes about. So I have Rij is ui at x, uj at x prime, average of that, and you want to take d by dri of that, and d by dri is related to d by dxi, etc. So this quantity here, so this is d by dxi of ui uj averaged, and you take inside this thing inside, so it becomes dui dxi uj, and this is always 0 by continuity. So any derivative of this with respect to one of these operators is one of these variables is 0. So that is helpful for you to remember, but not important for our purposes. I just mentioned that. So if that is true, then you can see what happens if I take t by the or I of that. So you integrate this, you have this, and you differentiate, you sort of have Ri only in this thing here. So what I will have is that you can write this as, say, K I R I or something like that if you want. Then you will simply have integral Ki Pij of k e to the power I k dot r dk. So if that is 0 on the left hand side, this is d by dri here, then this integrand will have to be 0. So you have the result ki Pij equals kj Pij equal to 0. So these, what I'm saying is Rijs and Pijs have certain properties, and I will discuss them later on for you. One other thing is, if you put I equal to j, say Ri of r, what is this? This is u1 ui prime, and if you put r equal to 0 in particular, this is simply equal to ui squared, which is the same as u squared, because this is u1 squared, u2 squared, u3 squared. This is the square of the entire thing. Let's do it that way. So this is just related to kinetic energy. Okay. So if you want, you can put this as, this is u1 squared plus u2 squared plus u3 squared. Now half of this is the kinetic energy. Now because, let's put it that way. So that is times 2. So this is the kinetic energy, and I have 2 times that. Basically, it's the mean square value. And let's see what else I should say. When you have that, see, I go to this formula here without all this. If you do that, RII equals integral phi of k dk, because this term is just 0, because r is 0. So the mean square energy here is simply spectrally spread out over k, and phi k is like the spectral density of the velocity, of the spectral representation of the kinetic energy over wave number space. So this is the kind of thing you might measure if you are measuring the spectral density, and you integrate it all over all wave numbers, you get the energy, and vice versa. You would have a relation relating the spectral energy to the kinetic energy. But this is all by way of definitions, and they have really very little to do with our task on hand. Our task on hand is basically to look at this equation without actually solving it, and deduce some general things. So let's write it as d by dt of Rij. This is equal to, I'll put this whole thing as Tij of R, and then plus Pij, let's say R and T. So this is also R and T. Yeah, it could change with time. So Pij of R and T, this Pij is that, and then I have plus 2 nu nabla squared Rij. So our object is to solve this equation for Rij, but we cannot do that because you have higher order terms here and higher order terms there as well. So the goal now is to try to interpret all this. Let's see if I can do that. So the first observation is, let's take Tij, this thing in the, this is the inertia term, so this is inertia, this is pressure, and this is viscous. Okay. Now Tij of 0, that is the nonlinear effects relating to Rij when you have shrunk this vector. So what do you have? You'll have, you see what you'll have. You'll have ui, uk, uj, because this dash will disappear because I'm measuring it at the same position, ui, uk, uj, and here I have ui, uj, uk, so that would be 0 always. Okay? So that has very profound implications. Here, this is equal to 0. Now, just as we defined the Fourier transform of Rij, you can define the Fourier transform of this Tij, and basically, I don't remember whether I have it here, so here's Tij, the Fourier transform of Tij. Let's invent a thing called gamma ij of k, of kappa, or k, e to the power I k dot r and dk. So if Tij of 0 will be equal to gamma ij of k dk. This is equal to 0 from here. So just imagine what this means for a minute. So I have the nonlinear term, and the nonlinear term has a Fourier transform. So all nonlinear effects added over the entire wave number space will be equal to 0. That is, we were talking earlier about, say, energy in this case as a function of, I wrote arbitrarily frequency, but since it's a homogeneous, spatially homogeneous flow, you want the wave number, which is this thing called k, wave number k, and there is nonlinear effect due to this term everywhere, entire wave number space. So some things are happening here, some things are happening here, some things are happening here, etc. But you integrate them over entire wave number space, that is identically 0. What this means is that the nonlinear effect is not going to change the magnitude of Tij or Rij, etc., but it is simply going to change the spread on the wave number space. So it may be what was here may be put here, etc., but if you integrate all the nonlinear effects of the entire wave number space, that is identically equal to 0. So the important thing about this is that the important consequence of what I just said is that what nonlinear terms do, or what inertia terms do, is to redistribute energy from one wave number to another, but not to take it out of the system altogether. So I have certain energy distributed in a certain way in wave number space. So initially it probably has a spectral density like that. Later on, the spectral density, due to the inertia effects alone, may be something like this, but always the area under this will be the same. That is to say, inertia effects has only the effect of spreading wave numbers, energy over different wave numbers. But it doesn't tell you whether the energy is going from here to there or from here to there or vice versa, or the combination of the two. But I will later on discuss with you about it. So, yeah, it's somewhat technical, so I'm sorry about that. Then let's look at PII. So the next thing is, let's look at PII. That is, I have this Pij here, this Pij. I'm going to put the indices and leave R alone. But you see what you will have. If you put I equal to j there, I have again the same thing. P ui prime, and I have P prime ui. But since this is homogeneous, it is really not going to make any difference, and that will be 0. That will also be 0. So what this suggests is that when you PII is just this, so P11 plus P22, etc., right? So when you sum up all the pressure effects for all the three components, the sum will be 0. So the pressure effects are only in terms of distributing energy from one component to another, as I was telling you this morning, but overall it doesn't take energy away from one R to another or one wave number to another. In fact, this relation is true. If you define a Fourier transform of this, you can show that it is true for each wave number. So if I define its Fourier transform like pi ij or something like that, pi ii at k equal to 0 at any k, that means the pressure effects not only distribute energy um, among the three components of energy, but they do it for each wave number. You see, so it's a very special effect of the pressure. So those are all very elementary things which I discussed very briefly, but you can say this more broadly. So here, if you Fourier transform this, I will have d by dt of phi ij, which is, and I have k and t, and I have Fourier transform this, and now here what happens? I have two derivatives of Rij, so I have drk, let's say, and in the Fourier transform, if you remember, I have phi ij e to the power I k r k. This is same as k dot r. K, maybe I shouldn't use k, just use L or something like that, L. So that's KL. So one derivative gives you a KL. So I have an I. Yeah. So I have one derivative gives me, with respect to RL, just IKL in front. Another derivative gives me another IKL in front. That means I have altogether I squared KL KL, that is minus KL KL. Okay, something like that. That's what I'll have. KL KL is same as K squared. So whenever I take the derivative of Rij with respect to one of the components of R, it simply means that I am adding, I'm multiplying this Fij by I times some k in the direction on which I have taken the differential. So basically, if you write the Fourier transform of this, I would have minus 2 nu k squared phi ij. See, I didn't write all these things. So in technical terms, what this means is that if I have a spectral density like that, in this fashion, then the dissipation, this is the viscous effect, is exactly this phi ij and nu multiplied by 2k squared. So k is increasing here, so k is 0 here. So you take this quantity multiplied by k squared, which may look like that, for instance. So this is the part, this is the viscous or dissipation effect. So basically, even if the energy is all contained like this at low wave numbers, the dissipative effect is concentrated at higher wave numbers like this, because you have a k squared multiplying, say k here is 0.01 and 0.1, 1, 10, like that. You can see what will happen. This is getting multiplied by a very small number, so you'll get there 10 to the power minus 4, and this will be 10 to the power minus 2 of that, and I have exactly the same amount, but I've drawn it on a different scale, etc. So that's how you will have. So I think this is the basic points I wanted to make about that. Now, therefore, what I have said is homogeneous turbulence in general, you can write down an expression for a second order quantity like this, and it will also have third order quantities in this fashion. And if we spend more time, and if I really felt I was communicating to you, we could spend a lot of time trying to discuss the properties of this Tij, etc. But I don't want to do that because it looks to me too technical, and I don't feel I am communicating that much to you if I do that. So let's do one special thing, and that is we not only now look at homogeneous turbulence, but also isotropic turbulence. That is to say, this any quantity like Rij that you can compute, like that one there, will not only be translationally invariant, like you take this here, move this anywhere, it's the same, but also reflectionally symmetric. That is, you move this like that, it would be the same, and rotationally symmetric. So that is, if I did I here, I would have to go around here, and then I would have to put J like that. So the configuration, this configuration is the same as this configuration rotated, but by some angle, and the properties of whatever we compute will not change. Now, that is a much more special case, because in any flow, let's say for example flow between parallel plates, you can imagine that because of the wall, it puts a certain symmetry on the fluctuations, and in fact it turns out very near the wall, for instance, velocities in this direction, not exactly at the wall but fairly short distance, velocities in this direction and in this direction are much larger than the velocity in this direction. But if you get to the center part of the channel, center part of this apparatus, they are becoming sort of very similar in all three directions, although not exactly the same. So you might say something like homogeneous and isotropic turbulence is possible there. And especially if you have things like the you consider things like the atmosphere, all the atmospheric turbulence, if you are above a certain number of meters in the ground, usually is very, very close to homogeneous and isotropic. So, because you have isotropy, there is a certain form that the Rij can take. Not all tensors can actually have rotational invariance and reflectional invariance. So let's consider Phi for instance. Any second order tensor in isotropic, any second order isotropic tensor can be written in this form. It can be written in the form A times Ki Kj plus B delta Ij. Delta Ij, you know what this is, delta Ij, the Kronecker delta, where I have this is equal to 1 if I equals j 0 otherwise. So what is the delta II, just for simplicity? What's that? What's that? It's 3, right? Because delta II means you have to, because my index is repeating, I have to do that, and each of them is 1, so this is equal to 3. And what is Ki? So what is that? Ki. This is equal to K1 squared plus K2 squared plus K3 squared. That's simply K squared, you know. You see what I'm saying? These are the components of the wave number vector, and you will have K squared. So that's the standard form of any isotropic tensor, and you can actually do better than that, because this is very general. Our second order tensor also follows the conditions of divergencelessness. That is the we have the condition dui or dxi equal to 0. This, when you translate to Rij, you remember I sort of wrote down this drij, this is equal to 0, and this I said when you translate to Phi is simply equal to Ki Phi equal to 0. So it should be such that this condition is also satisfied. So if I say Ki phi j equal to 0. This implies that I have a ki kj plus b. Now I have this multiplying by kj, ki, right? That's what I'm doing. So what is ki delta ij? It's equal to kj. You see, because delta ij will assume 0 values unless I equal to j, and therefore just this product is simply kj. Now, of course, you divide by kj. This must be true for all kj. Therefore, I have the relation, and this is k squared. So I have the relation b equals minus ak squared. So my phi ij is really not, it's very simple. It's minus a k squared delta ij minus ki kj. Yeah, something like that. Yeah, okay. So it's a relatively simple form. It has only one constant in front that you have to evaluate, for instance. And this whole thing is, if you solve for phi ij, because its form is known, you are only looking at the properties of this function, scalar function in front. And usually what is written, what is said, what is done is, in the wave number space, let's imagine a little sphere, and then you have a little elemental, so the sphere at wave number k, and then a spherical shell whose thickness is dk. Yeah. And imagine the energy contained in this band of wave numbers, and so, and write it as E of k. This is the normal thing. So what is phi I? You remember what phi I is. Remember what RII is. RII is ui squared, that is u1 squared plus u2 squared plus u3 squared. Phi I is the Fourier representation of that. And I said that if you integrate that, you get ui squared. So phi I is therefore the spectral energy distribution in the wave number space. And now I'm going to, because this A is unknown, I'm going to write it in the form of something else that I would like to deal with. And I have a sphere, and I look at a spherical shell of thickness k around the wave number k, and I calculate what that energy is. And that energy is this phi I times, you take this spherical shell has an area which is 4 pi k squared, and then because, yeah, it's all very confusing, I understand here. So phi I is simply u squared, but if I want kinetic energy, I just divide by 2, and so I have 2, and call this E of k. So E of k is just the energy density in a spherical shell of the thickness dk around k. So you put it here, instead of A, you put that one, and I have the representation that phi ij is equal to E of k over 4 pi k to the power 4 k squared delta ij minus ki kj. So my point is really that when you want to discuss the spectral distribution of energy in isotropic homogeneous turbulence, you only have to worry about this function E of k, which is simply the energy that is contained in a spherical shell of thickness dk around k. So your equation, all this complicated looking tensorial equation, will simply boil down to an equation for E of k. And that's the whole point. What's that? Where did I put k to the power 4?
The last line.
This one here? Oh, Four, what did 4 pi k squared is probably what it is, yeah. Now it is k to the power 4, all right, but yeah, it is k to the power 4, all right, because phi is minus a k squared, all this stuff you have, and this phi here is remember, if you take phi, it is minus a k squared, 3k squared here, minus ki, which is 1k squared. So I have minus 2 a k squared. So phi therefore is, a is therefore equal to minus phi or 2k squared, and that k squared got added here, and that's why you have k to the power 4. So similarly, you can do this for Rij. It's somewhat more complicated. This is equal to, let's say, C Ri Rj plus D delta Ij Ri. So that's the form it will take, and you will have to do that. Ri equal to 0, so d by di of that equal to 0, and you will now get rid of one of these constants or one of these functions, and then just as you have phi ij expressed in terms of one scalar function, you can express this also in terms of one scalar function, and I write that down for you because that is quite important, and that's what everyone measures, for instance. So without showing it to you, it's probably better not to write it all in detail. What you have is this Rij can be written in terms of one scalar function, u squared times f minus g over r squared ri rj plus g delta ij. It looks like I have two functions, but the two are related to each other. G equals f plus half r f prime. F prime here is simply equal to df dr. So I have just one function. And what is f? F is simply I have a position x and then a position x plus r. So this being the separation distance, these are two velocities measured along the separation distance. It's not any arbitrary orientation like that. Basically what it is saying is that a representation of any arbitrary orientation of velocities, all this here in isotropic case, just boils down to the correlation between velocities like that. Say up at x, up at x prime. P means parallel to the separation distance r, separation vector r, and average value divided by u squared. So that is the representation of that. And just as we interpreted E of k as a spherical shell energy, this is simply the correlation between two of them. So in general, in wind tunnels or something like that, you can measure, let's say I have flow going like that. This is all roughly isotropic and homogeneous. And let's say I measure one velocity there and one velocity component there, and multiply them, separated by a certain distance, average it, and I have f at with that separation distance. You measure it at another separation distance, etc., etc. It will look like f will look like it will look like this against r. when r is 0, that is the two of them are together, you will have the value equal to 1 by definition, because up times up is up squared, and I have here u squared, which could be p, or I say, yeah, let's make it p. Then it's just 1. And as you traverse the distance along this dimension, it will go down, and it will go down like that, go down monotonically, and it will. Our understanding is that it will never go negative, but nobody has been able to show that it is never negative. So that's how the behavior of R is. So the whole analysis will boil down to finding out what this F is, you see, because we wrote down this Rij. Instead of Rij, I can reduce it all to F. So the equation simply becomes df dt and all these other things. So I have next things and all that. Or if I write it in the Fourier representation, I just ask a dE of dt. The E I used yesterday is not the E as today, so that's that quantity. So you see, I have reduced this tensorial equation into simply scalar equations, and then we can try to understand that a little bit better and more easily. So if you got lost in some technical things, I'm sorry about that, but basically what I have tried to do is to show you how to write it all together, and I write this equation for F now, and we will spend the rest of the time discussing the properties of that. Okay?
So suppose at a distance r, I'm
Yeah.
trying to capture vortices of a size.
Yeah, yeah.
Then like every time, I mean, suppose I have, motion like this circular motion.
Yeah.
Every time I have a positive u on one side,
Yeah.
I'm very likely to have a negative u a distance r away.
Why would you do that?
Because I have a vortex.
Oh, in certain characteristic structures. Yeah, sure. Yeah, yeah.
So in those characteristics,
Yeah,
if
yeah.
those characteristic structures are the
Yeah.
winners,
Yeah.
I should have f going negative at a certain r.
Yeah. Okay. I think that's probably true.
So why does it matter?
But F in the classical homogeneous turbulence has never been measured to be negative. But for some structures, it's definitely conceivable that it could be negative for large R. Sorry? Yeah. So you can have negative values there also. But it's of course a very special kind of thing. So here is one drum, and here is the gap, and you have these vortices that are like that. And if you made F measurements along here, for instance, if you go into the other structure, you will have a negative sign. But that is not what we are talking about. I mean, in general, there are no structures, so well-defined structures in these flows, and there may be vortices of different sizes all together, and there may be non-vertical things as well. And that is part of the reason why homogeneous turbulence does not contain all aspects of turbulence, in particular when the structures are very strong. So if you look at flows like this, they are very strongly influenced by boundaries, and boundary conditions become a very important part of the problem. And so far I have really said nothing about boundary conditions, basically because I have a homogeneous medium, and technically a homogeneous medium is infinite in extent, technically. I mean, otherwise you cannot have homogeneity, it will break down somewhere. What came about? This one here? Oh, okay. Well, it's just like here, I have Fij and I reduced it to something very simple. I can do that. Since you asked, I might as well do that actually. So, So I have Rij, but the condition on Rij like that, right? So that I know. So any second order tensor can be represented, like I said, by this formula, and I have that, and therefore what will I have? If I do that, I have dri, dri, that will be, let's make it what I have here, f and g, makes it easier for me to write it. So you see I have dri, which is 3, right? You see what I'm saying? I'm going to derive this, differentiate this as product. This is a function of r, this is a function of r, and one variable of r, this is another. So I have first 3f ri, and then what will I have? Now I have not differentiated that, I have not differentiated that, I have differentiated that. So I have df dr ri, I have drij, which is a delta ij, therefore this is rj. You know, like that, you do the whole thing. Somehow you have to sit down and do it correctly, and what I will get is, I'll get 4f plus r df dr plus 1 over r dg dr. This is equal to 0. So you have to try it out. I think it's a good exercise for you to do it. So now therefore what I have is up at x, up at x prime, then ri and rj are simply, you see, this is separation vector, so ri equals rj, and ri or ri rj, this is equal to r squared. So I have therefore f r squared plus g of r, and this differential equation, this equation between f and r reduces one of them in the form of the other. So I can write the whole thing in terms of f, and this is simply equal to u squared times f of r, that quantity. So f of r will be in this form, f and g, and similarly I can write. So you see what I'm saying? So basically this gives you one relation between f and g, and you can eliminate one of these in favor of the other. So instead of f and g, you have only one f or whatever, and that can be written in terms of f, this little f, by going through this special quantity. So that's all. There is nothing else. It's simply, I can do it for you, maybe perhaps some other time. Let's have a tutorial on this. A lot of things I went through. So now the idea is, in the end, to show you that for the isotropic case, the advantage we have is that we have reduced everything to a scalar function and an equation for a scalar function, but it is still not just the equation for the scalar function, because you will have on the right hand side a quantity which is third order type quantity that you cannot solve. And without going through too much discussion, say f of r equals u squared 3 halves d by dr plus 4 over r of k of r, and I will tell you what this k of r is, plus 2 nu k squared u squared d squared by dr squared plus 4 over r d by dr of f of r. So it's simply that, and you can see all of them in some fashion. if d by dt of Rij just comes out to be like that. And this one here, which has 2 nu nabla squared, this nabla squared just turns out to have this form. And then I have this k of r, which is coming from a combination of these two. And just from here, this actually turns out to be 0. So what is k of r? Just as we defined f of r and g of r, f of r, k of r will be, let's say I have positions I and j. I take one velocity there, another velocity there, and a third velocity there. And I compute the statistical average of the product of these. So it will be up at x, up at x, up at x prime, the average, divided by u squared 3 halves. So I think this is a much easier equation to handle than a tensorial equation like that. And somehow k is the quantity that appears as a third order quantity when you're actually looking at the second order quantity, and that is the same as the closure problem. You can write an equation for k and etc. This equation has a very special place in turbulence, and it's called the Karman-Haworth equation. Karman-Haworth equation. If you have read the autobiography of Karman, von Karman, you will see this mentioned and how they derived it. You remember, any of you? So, I think this is true, at least as Karman said it. Haworth came to visit Karman. I think it was that way. Well, one of them came to visit the other, and they met at the train station to leave the other one off on the train. And Karman started writing on the surface of the train car with his finger because it was a dusty car, and he was beginning to write. And Haworth was very busy making the notes on this, at least as Karman says. And the train conductor started saying, "Come on guys, professor, it's time for the train to go." But then they started running with the train and still finishing the equation. That's it. Yeah. No, but this Karman was a man for drama, so I suppose that's only metaphorically true. So now, this is the equation you want to solve, but I am not going to solve this either. I'm only going to tell you what kind of inferences you can draw from here without solving it. Now, f of r has the property that it is 1 here, and then it will go down like that. But if you took r in the opposite direction, it will have the same shape because of the symmetry. It's isotropic flow, and so you will have the same shape. So this is f of r here. And because of that, at 1, r equal to 0, f is 1 here. And if you want to expand around 1, the next order term will be r square term, okay, because of the symmetry. So f at any r around r equal to 0 will be, r term will be 0. I'm doing the Taylor expansion, r squared by 2, f double prime at 0, etc. I'm not going to worry about the things. I'm only going to stay in this vicinity, and something like that is possible. And similarly, you can expand k around 0, and that turns out to be 0, a third order quantity. The magnitude at r equal to 0 will be 0, and then it has a Let me see what I have here. Page 12, page 13. So it will have some form which actually begins with r cube. I will write it down for you in a short time. Now, let's look at this f of r. Let's fit this r, the parabola here, like that. So that parabola will be like that. And that parabola will follow this f for a short distance, and then of course peel up from there, and it will be like that. So let's call this distance where the parabola hits as lambda, root 2 lambda it turns out, because I am going to say that r squared over 2 here, f double prime over 0 by 2, I want to put as 1 over lambda squared. So this is simply equal to 1 plus r squared by minus r squared by lambda squared. So f double prime is going to be negative, so I need that. So it will be something like that. Maybe not sure I need okay. So, and so on. So this lambda where this f, the parabolic fit near the origin for f meets this axis is called lambda, and it's a Taylor microscale. Lambda is the so-called Taylor microscale. So if you put r equal to 0 in this equation, what will I have? I have f is equal to simply u squared, up, up, right? But up in isotropic case is independent of which direction you take. So just say u squared, for instance, like that. So I will have an equation which is d by dt of u squared, and this k at 0 is 0. I wrote it here. And if you do all these things, then I will have minus 10 nu u squared f double prime 0. Because for f, I am just going to replace this quantity, and I'm going to differentiate, and I will get all that. Yeah. Yeah, this you have to go here. You have to go here, and now you have to do a little bit more work than I actually showed. So just as I did all this mind-boggling thing for getting the form of the second order tensor, you can actually do the same thing for the third order tensor. So I'm sorry, you have to do a little bit more work on this. I'm not sure how much I should do and how much I shouldn't do. As you see, I'm not really exactly enthusiastic about my own stuff here, because it's a lot of formalism. But I think basically, if I didn't do at least some of this, you would not know that the equation for the second order quantity can be reduced to a scalar equation. I think that's mostly what I want you to remember, and that's the form it takes. Normally, I would do this in elaborate detail, but I'm not sure that because you are certainly very inhomogeneous, I decided not to do that. Yeah, homogeneous turbulence. Yeah. So that's what you have to do, okay? I don't remember who asked the question already. You asked the question, yeah. So you have to write it down as a third order tensor in isotropic turbulence, can be expressed in terms of as we had for the second order in a certain form, and then you have to use the condition of incompressibility just as we used for the second order tensor, and then manipulate a little bit. You will get a quantity, and that quantity, again, going through its interpretation of what it is, it's UP, two places, all this kind of stuff, and then you will see that it is equal to 0. And in fact, it begins with the order r cube term. So it has a it has a form which is something like that, like that. Maybe not like that. So it's like that. That's how k of r will look like. So the first term it will have is of r cube. Yeah. Let me finish this somewhat mind-boggling exercises before we go to something interesting. And usually you want kinetic energy, which is u1 squared plus u2 squared plus u3 squared, which is equal to 3u by 2. This is equal to 3u squared by 2. So you multiply this by 3 halves, and that becomes minus 15. And this f00 prime is here. So I put it in here. I know I made some mistake here actually. It is u. This is the kind of thing. So d by dt is d dt. This is my other E. Let's simply say kinetic energy. Okay. So this is simply written in order to interpret for you what lambda is. Lambda is simply the scale, which in this definition like that will give you that. So if you recall, yeah, all this stuff is going back to what I wrote yesterday, which is d dt equals p minus d, and since p is 0, I have simply this quantity for you, which is this delta, this in terms of lambda. Okay, not very helpful, I know. What's that? What does it mean? It means just that. Actually, Taylor microscale is it's not very obvious how to interpret. But if I give you a little bit more analysis, which I might do, it boils down to if I have a signal, random signal like that, and I put a mean there, and I measure what the distance between successive zero crossings is. Okay, I have that, I have that. You see what I'm saying? So take all these successive mean crossing lengths and you average it, and that is roughly Taylor microscale. Now, so in some sense, what might you interpret this like? For example, this is a signal that you have measured at a given position in space. So you might have little structures that are going past you, and this may tell you something about those structures, the size of those structures. So for example, when the velocity is positive, you're maybe in the middle of a vortex in one direction. In the negative, it may be another vortex. Turbulence is not simply vorticity. I mean, you have to know that. Nevertheless, you might interpret it something like a mean distance of certain types of scales, mean size of some scale, and that is the Taylor microscale, roughly speaking. Now, it's neither the smallest scale in the flow nor the largest scale in the flow, The larger scales may be, for example, your signal may be sort of like that, it may be sort of like that. If it is like that, the larger scale would be maybe like that, and that's what you get from f of r. See, f of r will give you the distance over which you have a certain correlation, and in fact I am going to define for you. So the integral of f of r dr, this is some length scale L, which is sort of related to that. And this lambda is simply mean of all these distances, some of which may be large, some of them small, etc. Yeah, I'm not sure that there is any other better meaning I can give you for it, except through the definition. The definition here simply says rate of change of kinetic energy is kinetic energy divided by lambda squared by nu, let us say. So lambda squared by nu is a time scale. Is a time scale over which some significant dissipation takes place. So it's better defined like that than through anything else. Let me stop here and you ask me question. I think it's better. Yeah, okay. All right, let's do that.
How you obtain this kinetic energy relation? Using what?
Which kinetic energy relation? That one there? Yeah, I got it by putting r equal to 0 here. So when I put r equal to 0, I have d by dt of f0, which is u squared, which is kinetic energy, right? And this thing is 0 because r is 0, and I have here a lot of derivatives of f, and this of course will be 0, and you will have second derivative of f, and that's what I have here. Yeah, it's all, you should know that I have done this thing correctly. So there is r for sure, but when I put in for f this r squared by 2 f double prime, if you differentiate it, I will have one r here, and that r will be cancelled there, and I have that. You can do this if you want. I mean, basically, it will tell you, you differentiate it twice. I get all this cancelled out, and I have f double prime. I have here a 4 f double prime. Then this is 5 f double prime, and I have a 2 here, which gave me 10. And I multiplied by 3 halves, which gave me 15. It's even if I have made some error here, the final thing is all correct. Okay. So what else is not clear? I'm sure there are many things. Ask me some questions. I may be able to satisfy myself that you know.
About K of R, it was defined in as a average velocities over 3 points.
Yes.
Yes.
2 points, but 3 velocity components.
3 velocity components.
Yeah, I had written a sketch somewhere. So one velocity here, another velocity here, and a third velocity here. So up prime, and k is simply up prime over u squared to the power 3 halves. Thank you. What's that?
Why? UP and into UP. Why are those two supposed to be two different points?
They are not two different points. I should write it like this. Yeah, will that be okay? I was just drawing it over it, that's all. Yeah, it's not three different points.
Why the length scale? Why is the magnitude itself different in this case?
No, it's not.
It's not.
No, I didn't understand the question.
The way you are represented in the diagram, it appears to have different magnitude.
That is why I probably shouldn't do that. Okay, let's make it like that. I'm sorry, I confused you. Same UP, yeah. And I am so used to writing one like that and another like that, thinking that this is the same as that. But I know you can get confused. So okay, this is let's put it more correctly. One UP, another UP, like that.
Now, when you did the Taylor expansion, I don't see how this goes to zero. Even
No, Taylor expansion doesn't go to zero. It has nothing to do with that. So that's the F, right? You're trying to Taylor expand it here. So I have F0 and then R F prime 0, which is 0, and then I have R squared by 2 F double prime at 0 plus higher order terms. This one here. This one here. Yeah, this will take a little work. Just as I did for F all the way through, you have to do all the way through for K. You want me to do that? Yeah, you should do that at home. It's not going to be easy. But you can do it. This is why I sort of shoved it aside and simply asked you to take me on trust. Just as I did it for F, you can do it for K, and it'll be something like that. So what I was doing here was just plotting this quantity here. So I know what F double prime is, so I fit a parabola there and simply extend that parabola down all the way. So it's a parabola that fits the central part of f of r. Instead of going like that, it will of course go here, and it hits the origin or hits this axis at some point, and this defines for you a length scale, because r is a length, and in fact that is same as lambda. Okay, and that's all. So that's the actual definition of lambda, how you compute it. But the interpretation I gave as a zero crossing length scale is not contained here, but it is something I gave you from my knowledge of whatever else. I think you shouldn't get bogged down by details, but basically this one here. So let's see what that f of r is like. So f is this thing here, right? So I have a up. That's the same graph. Same graph, except that I only wrote one part of it here. But if you did it for r in the opposite direction, it would do exactly similar. So what f of r will tell you, if you have it, is, let's say I have this distance, and I measure the correlation between them. Let's say for some r equal to r1, say r1 here, it is giving me a value 0.4, for instance. So it says that there is some 40% correlation between what happens here and a distance r apart, right? Isn't that what it says? So this whole side, this graph is telling you the extent of the spatial domain over which things are correlated, velocity fluctuations are correlated. So statistically speaking, if velocity here and the velocity here were uncorrelated, that is, they had no relation to each other statistically, then any f that you measure between them would be 0. So it is 1 because when r is 0, the two of them are the same, therefore they are most correlated. And if you take it away, further and further away, then the correlation will die down because things happening here are not related to what's happening in Bangalore, I mean very far away. So it will vanish, but it will vanish in some particular way, and I don't know what that particular way is, and that's part of what we want to solve. If we can, we want to solve the shape of that function, and I'm just trying to say, well, let's try to get at least the shape of the function here, what shape it will take and what kind of relation it will have, and that's why I started writing the thing relation at r equals 0.
In the case of like general shear turbulence, so you will have to end up solving the entire correlation function as per that original equation, or will there be?
Yeah, in the case of a shear flow, for instance, you don't have this isotropic symmetry, so
Are there ways around that? I mean, like, can you make some assumptions and, or you have to solve for all the?
you if you are interested in second order quantities there, basically you have a second order tensor, and you may reduce the number of independent quantities depending on the symmetry of the problem. In the symmetry where this, which is spherical, you can represent all of it by one scalar function, which is not very surprising because you take the correlation between here and there in this direction must be the same as the direction, the correlation in this direction, etc. And so you basically have one quantity, one scalar quantity of a scalar variable in this case. But if you want to look at, let's say, shear flow, then you have certainly the direction parallel to the stream is different from the direction perpendicular to the stream, and it is also different from the direction which is perpendicular to both of them. So through independent directions, and so your quantity will depend on each of those variables. And furthermore, the correlation between velocities in this direction is going to be a different function from the correlation in the vertical direction. So not only do you have three, in the argument has three variables, so if you construct a quantity like f, it will depend on the vector r, not on just the separation distance, but it will also depend upon which component u, v, or w you are making those things for. So not all the correlations need to be measured, and nowadays especially you don't have to measure most of them, because initially the motivation for this is to get some idea of the structure in the flow. A lot of people have spent a lot of time trying to measure correlations in different directions and interpret those correlations in terms of structure. So as Rama was saying earlier, if you have a certain type of structure, it gives you a certain type of correlation. So with that in mind, you measure correlations in different directions and you sort of infer what the structure, major structure in the flow ought to be. Nowadays, you sort of can compute all of it, therefore you don't really need a whole lot of these correlations and things like that. So this is only sort of a basic theoretical underpinning of how things work. So if you are simulating a shear flow, for instance, you already know near the wall there are hairpin structures, etc., which people didn't know earlier, early before 1956 or something like that. And then people in Cambridge in particular measured these correlations along the stream, vertical to the stream, etc., and they inferred certain average structures. And if you look at Townsend's book, Townsend 1956 or thereabout, the first chapter is about correlations and things like that, and later on he deduces a structure which has this feature near the wall. He infers a structure like this, and it is all deduced totally by correlations. He had no No idea. He had not seen any of them himself, as far as I can tell. But you could do that. You could do that in some way. For example, as Rama was earlier pointing out, let's say your f of r goes like that. And then you know that you have a certain structure that will give you a negative correlation. And then you also consider f in this direction, so that will tell you what the structure might be in the opposite direction. And if you look at this paper by Kovazne, Gibbons, and Blackwelder, JFM, volume 40, I think 1971. There's only one paper by these three authors, so even if I'm wrong, it will be okay, but I'm pretty sure this is correct. So what they do is they measure correlations in all possible directions in the boundary layer in which you are interested, and they infer the kind of structures that could be there. So that is the experimental use of these correlation functions. Theoretically, I couldn't care less if it was not f. Anything like that would be okay for me. But it is just showing that I have a very simple equation relative to the tensorial equation. Do you have a question?
K, sir, for like 2 points are if f value is high and it is more correlated, so K will also be high because K will also be.
No, K is not, because it is squared here. It's a bit more complicated in interpretation. Here you have a squared quantity, which is not the fluctuation. It's not the fluctuation like that, but it is this kind of thing. And how that is correlated with the velocity here. So it is not simply related to the velocity correlation. So you have to think a little bit harder to make sense out of that.
So what do you mean by negative correlation?
Negative correlation means if you are smiling, somebody is frowning, and if somebody is frowning, you are smiling. Just the opposite of. So if the velocity is going up like this, if the velocity is going down like this at some other point, then these two are negatively correlated.
Why it is that difficult?
What is the difficult?
Why it is so difficult to see? Why people are not seeing?
Why they haven't seen negative correlations? No. I wasn't saying that. What I was saying was, in homogeneous turbulence, if you measure f, it's always positive. That means there are no anti-correlated quantities in the one direction. So if this is going up like that, things are always going up, but little less so. But if you measure the other correlation function, g, which I wrote down here, g equals f plus half r f prime, and g is, there are 2 points here. One is their velocities are measured normal to the separation thing. This g is negative. This g goes like that and then goes like that. Maybe not that much, but like that. So here you see what will happen. So let's put it this way. I have a medium like this, and the velocity is doing one thing here, and it is doing the same thing up to a certain distance, right? If it is going down here, the velocities are all going down here up to a certain distance, although less and less correlated here. Now it has to go up in this direction now because of conservation of mass or something like that. You see, for example, think of this as a channel, and then you measure g. It's some kind of imaginary channel. So the mass flow along here has to be conserved. So what is going up has to come down, kind of thing. because the mean velocity is 0, it's all fluctuation. So in some sense, g has to be negative like that. So if it is, if the velocities are all up to a certain distance correlated, then they're anti-correlated a little bit later. You are not convinced, I know that. You have to think through this yourself. It's not much harder. I mean, I don't know anyone who explained any of this to me, so. No, that's not clear. I mean, that some functions can go negative and some can go positive. There is no proof that f of r should always be positive, as far as I know. But as far as I know, nobody measures it anything differently. Whereas g by construction is both positive and negative because of this. If you put a monotonic function, monotonically decreasing function, and then you compute this, you see that it will have to be negative at some point. You can construct any correlation you like. For example, you can construct a correlation like that and a correlation between velocities like that. Okay, you can do that. But the point in isotropic turbulence is this will be R1, 1, 2, right? I mean R1, 2, yeah. Because at the ith point it is in direction 1 and the jth point it is in direction 2, so it's R1, 2. So I have R11, R12, R13, R21, R22, R23, etc. So I have a matrix of 9 numbers, but in isotropic turbulence, all of them boil down to or can be reduced to this f or g, and from that you can construct anything you want. And where do I construct it? I can construct it here. I can construct it by my definition. Rij is f Ri Rj plus g delta ij. So I have that. So my R11, this is R. Okay, so R11 of R1 is really f. That is velocity components in the direction 1 and the separation direction also in 1. That is f. Now R12, you put I equal to 1 and j equal to 2. So this f R1 R2 plus g, the g will go away. So I have that, and f now is represented in terms of this f, and somewhere is that relation. So there will be something relating to f here. So R12 can also be represented in little f. Similarly, everything else can be represented in terms of f. Anything you want. So that's the nice thing about isotropic turbulence, because you have just one quantity to worry about. And similarly, if you take spectral density, for example, oh, by the way, if I get R12, let's take R12 will be 0, right? Isn't that right? So anyhow, so yeah, basically you can represent everything in terms of f. So similarly, just as you did here, in the spectral space, phi ij is E times all this k squared ki kj minus k squared delta ij kind of thing. And so phi 11, for instance, phi 11 is equal to E, this is k1 squared minus k squared. So you will have some such a relationship. And you can represent everything in terms of phi11 or E of k in general. So what it means is, if I know how much energy is contained in the spherical shell as a function of this k, see, I go to higher and higher k, the spherical shell also becomes bigger and bigger. Then if I want the spectral energy, for example, in this direction, spectrum of energy just in this direction, by symmetry of construction, it is related to F because of the symmetry in the problem. And it would be the same in this direction as this, and same in this direction, etc. And you can also ask what is the spectral density of a quantity like U1, U2 average, and you can get all of that through this E of k and this formula here. Anything you want. Okay, I think we can stop here. Tomorrow what I would like to do is to take you through not the solution of this equation, but to the most important phenomenology in turbulence known as the Kolmogorov phenomenology. And as an introduction to that, let me put it this way. So I have an equation for phi or equation for rij, which reduces to equation for f of r in this case and E in this case. We still cannot solve it, and therefore we do not know what form it will take. But there are some general arguments that you can make, as Kolmogorov did, which will tell you what the form of the spectral density is, at least in some range of the wave numbers. And I think that is sufficiently valuable for us to learn about, because the general arguments made there are so powerful that you can use them to construct your own theories for various other quantities. And it's not very hard once you understand the concept. And so tomorrow I will go through that, and then I will try to show what the problems with that theory are and how far you can go with it. I think that will bring us to a point where basically everything you know about homogeneous isotropic turbulence can be cast in theoretical terms. And after that, I would like to take a particular flow, which is maybe a flow between channel or something like that, and go through that, sometimes making reference to homogeneous turbulence, and most of the time just not doing that at all. And that's my plan. And therefore, what I plan to do tomorrow should be of very general interest to a lot of others in, say, condensed matter physics and things like that, because generally the way the field has evolved in physics, you remember people know a lot about atoms, and people can compute things both classically and even quantum mechanically if you have a very small number of degrees of freedom. For example, quantum mechanics really has been successfully calculated or been used to calculate a simple atom like a hydrogen atom, where you have very few electrons and things like that. The same thing cannot be done for nitrogen even today because it's just too complicated. And so physics has been very successful when the number of constituents you deal with are very small. Two bodies colliding with each other, that you know very well. You can compute the whole thing. Three bodies already is becoming complicated because of chaos and things like that. And if you have many body problem, you don't really know how to do this, really. So physicists have sort of moved on with interactions of small number of degrees of freedom. But the problem in turbulence is that you have a very large number of degrees of freedom, many scales interacting with each other, and one doesn't know how to deal with all this. The technology is not developed that much. There are other problems where many degrees of freedom interact with each other, but traditionally, historically, turbulence is the one that really was looked at from that point of view. And when you have a large number of degrees of freedom, of course, you can do statistical mechanics, but it is not the usual type of statistical mechanics. And the idea of scaling first came into physics via turbulence. For example, you always ask, if I increase something like a size of the system or something like that, how will the interactions change? You may not know exactly what the interactions are, but you can always say how the interactions change, in relation to something else. And that idea of scaling, which is related to the work that I will describe tomorrow, was originated in turbulence and has since gone on to be used much more sophisticated way in critical phenomena. For instance, critical phenomena that occur near the critical point, and there are issues of renormalization that people have been very successfully able to do, and there's a lot of universal scaling that people developed in that area. So because of that force of universality near the critical point in that field, there feedback into turbulence asking for whether there are universal exponents near the critical point, which may be very difficult to define here. And but turbulence has gone much further than critical phenomena in another sense, and that is most critical phenomena deal with equilibrium situations, and you have universal exponents and different order exponents, different order quantities have the same exponents more or less, that is same multiplied by some number or something like that. But in turbulence it looks like different order moments follow, each of them follows its own happy scaling, not related to the scaling of other moments. So you have what is known as the multiscaling phenomena, or multi-fractal scaling if you like. So this is not very common in critical phenomena. So in that sense, this has moved the field a little bit further. So a big part of the exercise has been to compute these, certainly numerically, and also some theoretical understanding of that problem. And that brings you almost to the frontier of the field in that direction. Of course, knowing exponents doesn't mean that you know what the field does or what the fluid field does. Therefore, in that sense, it has no implications on the practical sides of things. But on a fundamental level, it's very important. And on the practical side, now the most important advance that has happened is in the area of computations. You can compute the flow, in great detail now because of the huge computers available, and you can do direct numerical simulations on the one hand, or if the flow is very big, as most often is the case, you do the so-called larger simulations, or the RANS type modeling that I described earlier today. So I will say my goal is now to go through the Kolmogorov phenomenology and take you on the one hand towards the frontiers of say exponent business in one type, and on the other type to take you to the computational end that you can use to understand, if not understand, really compute the flow. So those are the two branching points for us. I'll do one tomorrow, and with some luck the day after tomorrow, I'll try to do the other.